Hi everyone, my name is Roland. I'm on the web dev team here at the Cognitive Science Student Association, and welcome to our first technical workshop of the quarter. Today we'll be working on an introduction to R and linear regression. So go ahead and use that QR code to sign in. You will receive 10 points for attending this event. And yeah, I'll give you guys a second with that and then we'll get started very shortly. Okay, quick poll. Who here is a machine learning major? Perfect. And who here has ever worked with R before? Okay. Who here has performed any kind of regressions before? Oh, okay. So this will be a first for many of you. How exciting. So, what are we doing today? Today, we'll be going over some basic data science principles, which will allow you to perform statistical inferences. From there, we will move on to an overview of machine learning, and then the fun part, we'll be working with R and R Studio to perform regressions. And then at the end, we can do a quick recap, a quick review of what we covered in the workshop, and then we're going to have a Q&A. Go ahead and ask any questions regarding R, regarding our regressions, regarding anything we did today, or anything within CSSA or UCSD as well. Who's ready for this? Yeah. Let's get started with data science principles. So what even is data science? Data science is comprised of two aspects. We're going to start with statistical methods, and these are just to solve scientific problems. And the main question that statistical methods are trying to answer is, what is statistically the most probable outcome? So we use data science to find patterns and then use those to make a prediction about what is most probable. And that aligns directly with statistical inference, when data is drawn from a sample and then applied to a population. We use patterns within this data to draw those conclusions and make assumptions about this population. Do we have any questions so far? We're good? Perfect. So this is a quick overview of the data cycle. We will be performing all of these tasks today. Let's start with importing. This is when you just import your data, usually a large data set with many columns and rows, which is why we must tidy them. We're gonna choose certain variables that we're interested in, and then this is the fun part. We start transforming them and visualizing them in graphs, in charts, in histograms, and then we use those visualizations to create a model and predict future outcomes. And at this point, we can truly understand the patterns within the data, and then we will communicate these patterns outward. I'm sure some of you are very familiar with this cycle. So there are several types of data. We're going to cover two specifically in this workshop. Let's start with categorical data. These are when there are certain categories within your data, certain labels. A great example of this would be types of students and their majors. So in this data set, we would have names of students and then their majors. Important factors in categorical data is frequency, which is the number of times the category is observed. In our example, that would be how many machine learning majors are there. And then there's relative frequency, which is the sample proportion for each category. We're seeing what percent of this data is comprised of machine learning majors. On the other hand, we have numerical data, which is data comprised solely of numbers. An example of this is, say, students' names and their scores on an exam. And two important factors, again, are location and central tendency. These are different average values within the observed data. In our example, it would be the average score on an exam. And then spread is also another important factor. This is just the range of all observed values. So what was the lowest test score and what was the highest test score? Under range, there are certain measurements that are important. Sample variance will describe the dispersion amongst the spread. And then sample deviation is just the root of that standard variance. I know these terms can be a bit technical, but don't worry, you will not be performing the math, the computer will. Any questions so far? Okay. Let's move on to statistical inference and probability. So probability is just the measure of uncertainty to generalize data for a population. An example is, what is the probability that I will be late to lecture? I'm not sure if I'm going to be late yet, but I'm also not sure that I'm going to be on time. So there's some kind of uncertainty there, and we can assign a numerical value to that. Sample space, complement, union, and intersection are other types of measures within probability, which we will not cover, but I did put it there for your reference in the future. And with probability, we have variables, which is when you assign a numerical value to each possible outcome. In the example before, there's an outcome that I will be late to lecture, and there's an outcome that I will be on time to lecture. We can assign said numerical value to those two outcomes. Under here are two important things. Discrete random variables are countable or tangible sets of values. So an example of a discrete variable would be the number of siblings you have. You can have 0, 1, 2, 3 siblings, but you can't have 1.5 or 2.6 or 3.3 siblings. So there are discrete categories of these variables and they cannot overlap. Opposite to that are continuous random variables, which are uncountable or infinite sets of values. An example of this is your height. You can be 56 inches tall, you can be 72 inches tall, you can be 63.2 inches tall, you can be 63.255 inches tall. Continuous variables have infinite amounts of values, and they can go on and on and on forever. So those are two very core concepts between variables, discrete and continuous variables. And we'll be working with both to perform our regressions. With probability, there are distributions. So random variables have certain distributions that they follow. Two important ones are the Brunelli distributions, which are just binary random values for a set amount of outcomes. In this case, you are choosing how many outcomes are possible. And that carries over to binomial distribution, which is just the sum of all of these trials. We also have continuous probability distributions. These are a bit more easier to understand. Lower tail probability is observing a value less than a chosen value, and the upper tail is observing values more than a chosen value. An example is looking at the spread of test scores. How many students scored less than 65%, and how many students scored more than 65%. The other terms on there we will not cover, but I do have them there for your reference. And again, if this sounds a bit too technical, the computer will be doing the math for you, and you just have to look at the models. Here's a really interesting rule that is very common within regressions. It's the 68, 95, 99.7% rule, where 68% of values fall within one standard deviation, represented by the green arrow here. 95% of values fall within two standard deviations, represented by the blue arrow. and 99.7% of values will fall within 3 standard deviations with the yellow arrow here. So this gives us a normal distribution and makes it very easy for us to make predictions that can be applied to larger populations. Let's move on to machine learning, the exciting part. Who knew that machines can learn? But what even is machine learning? A possible definition by Kevin Murphy, who wrote the book Machine Learning, A Probabilistic Perspective, describes it as a set of methods that can automatically detect patterns in data and then use the uncovered patterns to predict future data or to perform other kinds of decisions under uncertainty. So this is very similar to how humans make decisions. Every day you are making thousands of decisions that you perform under uncertainty. You are not always 100% confident in the decisions that you're making. But through your lived experience and previous knowledge, you have detected patterns within everyday life and used those expectations to create your decisions. The point I'm trying to make is that humans operate under uncertainty all the time, and that's the exact same thing for machines. We all know that ChatGPT is not always correct. There is lots of uncertainty, especially in language models, that these machines and these algorithms have to perform. And there are always 3 aspects to any machine learning task. The first one is training data, which is when algorithms use data from previous observations to build predictions of the future. This is usually provided as a data set or as a database for the algorithms to learn. The second aspect is modeling patterns. From the training data, we capture patterns and choose how to model these sets of data. And then we use the training data and the patterns from that training data to forecast predictions, where the model will define the probabilities of certain outcomes, and we'll use that to forecast decisions. So these are the 3 aspects of any machine learning task. You will be performing all 3 of these actions today. How exciting! So, let's cover a few problems that machine learning attempts to solve. The first one is the classification problem. These are made of discrete categories. Who wants to tell me what discrete categories are? Yes. Discrete categories describe categories that have a set amount of outcomes. From the example earlier, you can only have 1, 2, 3 siblings, and you can't have 1.5 or 2.4 siblings. And the classification problems and its outcomes are used to make a decision about something. An example is, should I go to lecture or not? The 2 discrete categories would be yes or no. On the other hand, we also have regression problems, and these are made of continuous categories. Who wants to tell me what continuous categories are? You guys are doing amazing. Continuous categories are those with infinite sets of values. From the earlier example, it could be height. You could be 72 inches. You could be 83 inches. You could be 74.6 inches. You can be 74.65 inches. There are an infinite amount of values in these categories. And this is usually used to predict an outcome. Like, what is the most probabilistic score that students will receive on an exam? How are we doing so far? Do we get the two major differences between classification and regression, discrete categories versus continuous categories? Perfect. So let's move on to supervised learning. This is when labels and categories are given to the data set, meaning that the training data contains categories and that the algorithm just needs to find patterns within those categories and the variables. This is on the opposite spectrum of unsupervised learning, which is when the provided data set is completely unclustered and the model must find the labels, categories, and patterns itself. How are we getting this so far? You guys are doing amazing. Perfect. Okay. So, the most exciting part, let's get to regressions. Our first type of regression is a simple linear regression, which is trying to explore a potential linear relationship. On the y-axis, there's usually a numerical response value, and on the x-axis, there's usually a categorical explanatory variable. And here, we're just trying to find a linear relationship between these two variables. Pretty simple, given the name. Let's move on to something a bit more complex. Multiple linear regressions attempt to explore a potential dimensional relationship. In this case, there's usually one numerical response variable on the y-axis and multiple explanatory variables on the x-axis. So here, instead of just finding one linear relationship, we're trying to find several linear relationships between the multiple variables on the x-axis and the y-axis. But the best one of them all, least squares regression. This type of regression attempts to find a line of best fit. And there's a numerical response variable on the y-axis and a numerical explanatory variable on the x-axis. And when compared to simple linear regressions, least squares are trying to minimize the distance between every point and the line of best fit. So instead of just trying to find a potential linear relationship, the line of best fit attempts to capture as much of the data as possible. In our example here, is trying to minimize the distance between each of these points and said line of best fit. Pretty cool, I would say. So now that we got the concepts down, let's actually make this happen. We're moving on to R and R Studio. R-S-T-U-V. You guys get it? Thank you. Thank you for laughing. Yes, I appreciate it. So R is a programming language specifically used for statistical computing. It's a software environment for statistical computing and graphics. And we're going to download it at this link right here, but not quite yet. Before we do that, I'm going to explain R Studio, which is the IDE that we're going to be using to work with R. R Studio is just a set of tools built to help you be more productive with R and Python. So R is a programming language, and R Studio is the environment that will be interacting with R. Okay, so everyone, if you haven't already, pull out your computers. We're gonna do some live coding. Very exciting stuff. Okay, now that everyone is ready, let's start by going to cloud.r-project.org. I personally am on Linux, but I will go through the Windows and Mac OS installations with you guys. So if you're on Windows, go ahead and press on Windows. You're going to want to install R for the first time, and then download the exe file. Once it's downloaded, go ahead and go through with all the default installation options, and you should be able to see the R compiler on your desktop. If you are on Mac, go ahead and press on Mac OS. If you have a 2020 Apple Silicon or newer MacBook, go ahead and use the ARM package. And if you are on Intel, make sure to use the x86 64 package. You're going to want to download those and complete the default installations as well. Now that everyone has R downloaded and can see the R compiler, let's download RStudio because the compiler is not that cute. We want a nicer IDE to work with R on. So go ahead and go to postit.co/downloads. We're going to want to download RStudio and not RStudio Server. Perfect. And it seems like step 1 is to install R. We already did that. Go ahead and install R. I believe if you're on Mac or Windows, there should be just an option right here. But if not, you can scroll down and choose your OS and download it. And you go ahead and go through with all the default installations as well. So now that we have RStudio installed, go ahead and open the IDE, and this is your integrated development environment. On the left side, you can see the console. On the top right, we have the environment of data. So right now it's empty. And then on the bottom, we just have a file explorer. We're going to start by making a new R Markdown document. Go ahead and press that. And if it prompts you to install any packages, go ahead and say yes. It will start installing in the console, and then eventually the new R Markdown prompt should come up. We're going to call this document Intro to R and Linear Regression. We're going to keep the default output as an HTML because, in my opinion, that renders our graphs most accurately. Go ahead and press OK. And then boom, welcome to your R code. So here we can see the title, we see the output and the date. And then very interestingly, R code is separated by chunks. So lines 7 through 9 are considered an R chunk. This is the R setup chunk, and it's initialized by starting with 3 backticks and ending with another 3 backticks. Here we see a comment represented by 2 hashtags, and then below that is just plain text in the R Markdown document. This is actually the default introductory text that comes with every document. We're going to delete lines 10 and onward for the sake of this workshop, but you guys are welcome to read that on your own. So before we even get into coding, we need to install some libraries into our IDE. So go ahead and go to the console and let's install.packages and then parentheses C parentheses double quotations. We're going to need to install tidyverse, and then we're going to need to install ggplot2, and then we're going to need reader spelled like that. Go ahead and press enter, and then the packages should start downloading and installing in your console. I already have them downloaded, so I will not be doing that. Once that's all done, go ahead and let's fill out our initializing R setup chunk. So now that we've installed those libraries, we need to import them to this specific document. So let's type library, parentheses, tidyverse, and then library, parentheses, ggplot2, and then library, parentheses, reader. Perfect. So that is our R setup chunk. We are finished with that chunk, and let's start a new chunk with 3 backticks, curly brace, and let's just name this R. So now that our document is all set up and ready to go, let's start by importing a data set and then visualizing that data within R. So we're going to be working with a data set regarding babies at birth and just certain vital signs that they have, like birth weight, gestation rates, and whether or not their mother was a smoker. So we're going to create a variable called babies, and we're going to set this equal to the reader function, the reader library, and then the function read_CSV.
And we're going to be using this data set provided by the UCI Data Academy, found at https://uci-data-academy/slides/main/data/babies.csv. And you guys just wrote your first line of R code. Let's not forget to close off the chunk by adding 3 more backticks. And let's see what this output looks like. So knit is the compile function in RStudio. We're going to knit this markdown document as an HTML file. So let's knit to HTML. Let's save it in my documents. We're going to name this again Intro to R and Linear Regression. Save, and let's see what it looks like. So the rendering was successful. And here's our document. So here's the R code we wrote, and ooh, let's look at this output. There seems to be 1,236 rows and 9 columns. That's a lot of information. And these seem to be several columns: case, birth weight, gestation, age, height, weight. Interesting, interesting. So our data is now in the R program, but this doesn't really tell us much. So let's see what else we can do with RStudio. So that was importing the data. Let me add a comment. So that was importing data set into R. Let's see some things about this data set. So we're going to be using the glimpse function, glimpse data set. And that's just going to be glimpse, and then the data set, which is going to be babies. Let's see what this looks like. We're going to knit as an HTML again. And ooh, look at this. We get a quick glimpse, you could say, of the data set. So again, we have the same rows and columns, and it seems like those rows are case, birth weight, gestation, parity, age, height, weight, and smoke. And then we can start seeing, look at these datas. Case 1, 2, 3, 4, 5. So it looks like the first case was born at 120, second was born at 113. How interesting. So again, we are just viewing this data set within R, but let's do something even more fun. Let's see what R can do statistically. So let's summarize this data set. What measurements can we get from it? So we're going to call it a summary function, and then the data set again is going to be babies. And let's see what this looks like. How interesting! Isn't this so fun? We have all these statistical measurements from the data. Look, it seems like the minimum age of someone who gave birth was 15. It's quite young. The average was someone who's 27.26 years, and the maximum was 45. Interesting. And minimum birth weight, 55 ounces, I believe. Maximum 176 ounces. Whoa. And look at this. There were 742 mothers that didn't smoke, but 484 of them were smoking while pregnant. That is crazy. But isn't this so cool? From this huge data set, we have no idea any patterns are going on. And then just a quick summary, we can start getting the minimums, the first quantiles, the medians, the means, the third quantiles, the maxes. So fun. So why don't we put a few of these measurements onto a graph. That will be exciting. So let's start by graphing a single categorical variable. And we're going to be using the ggplot function for this. So it's going to be ggplot, and then our data is going to be babies. And then ggplot has a function called aesthetic. So AES. Our x-axis is going to be, let's say it's going to be smoke. And then what would be the best way to graph this, a single categorical variable? Who thinks a bar graph would be good? Unanimous vote for bar graphs, so let's do that. Plus, we're going to be calling the geometry function, and let's make a bar graph. Let's see what this looks like. Whoa! R just made us a graph, guys. Look how cool. So, good thing it seems like most mothers were not smoking while pregnant, but a large enough, a statistically significant amount of mothers were indeed smoking while pregnant. So, and then over here we see that there were a couple that didn't report their smoking status. How cool, right? So that's a categorical variable. What about a numerical variable? Let's see what that looks like. So let's graph a single numerical variable. Who wants to guess what function we'll be using? Yes, ggplot is. And who wants to guess what data we're using? You got it. It is exactly babies. And then for our aesthetic this time, let's choose birth weight as the x-axis. And what kind of graph do we think will be best for this again? So we have a bunch of numerical variables and it starts with an H and ends with gram. A histogram, yes. So we're going to be calling again the geometry function, and this time we're making a histogram. Why is there an X there? Oh, it's gone. Perfect. Let's see what this looks like. Whoa! So from this one data set, specifically birth weight, we can see that the most common birth weight was around maybe 120, 125. Very good. And this does seem to follow somewhat of a normal distribution as well, where there's a fair amount of dispersion amongst both sides and the peak in the middle. Very nice. Our baby data set is pretty normal. Very cool. Let's do something a bit more fun though, because this is all gray, which is fine. But let's add some color to our graphs. So under the same graph, let's do a bit of adjustments. So using the geometry function, let's set the bin width of our graph. So that's the width of every bar. Let's set that equal to 2. And then let's add a color. So that's going to be fill, and then equal to, what color are we thinking, guys? Pink it is. Pink, I believe it's pink 1. Let's see what this looks like. Oh my god, our graph is now pink. How fun. And look at this. After we changed the bin width, the the graph looks a bit different. Now that each bar is smaller, you can get much more precise representations of this data. And the peak we had before, it's still around 120 and 125, but we can see that there's actually almost 2 peaks and not just that super simple dispersion that we had before. Very cool. It's the same data, but we're getting different graphs. So that was single variables. Let's move on to multiple variables. Let's graph 2 categorical variables. Who wants to guess what function we'll be using? Yes, ggplot is. And who wants to guess the data? The data is going to be babies. And this time, let's set our x-axis to smoke again. And let's fill it with parity. And let's put this in a bar graph. Whoa! Our graph is a lot more colorful than it was before. And we can see that the first variable is smoke, and the second variable is represented by colors, parity. Parity just describes whether or not the fetus was able to reach a certain gestational age. And we can see that for the mothers that didn't smoke, most of them were able to go past that gestational age. Whereas for people that did smoke, a few less were not able to make it past that certain age. So here we have 2 categorical variables represented in the same graph. Isn't this just so exciting? But now that we have 2 categorical variables, let's see what it looks like to have 2 numerical variables. So graphing 2 numerical variables. Who wants to guess what function we're using? You know it. It's going to be ggplot once again. Our data is going to be babies once again. Oh, sorry. And this time, we're going to have gestation as the x-axis. And for the y-axis, let's have birth weight. And what kind of graph should we use for 2 numerical variables? If there are infinite amounts of variables on the y-axis and both the y-axis and the x-axis. How about a scatter plot? That would be super cool. So geometry, and then it's called point, but it means scatter plot. Why is there an x? Oh, it's gone. And let's see what this looks like. Oh my god. Look how cool the scatter plot looks. And now that we have said scatter plot, what do you guys think we can do with this representation? Yes, this scatter plot is perfect for simple linear regressions or even least squared regressions. You can draw that linear relationship through the graph, or you can find the line of best fit as well. But unfortunately, we have reached our time limit for this workshop. We have already gone a couple minutes over. I am so sorry, but at our next workshop, we will be performing a linear regression on this exact scatter plot, and you guys will be fully equipped, RStudio ready, to perform both linear and logistical regressions. So I will see you guys at our next workshop.